Okay, everybody, we're going to get started here. Um, it was pointed out to me that I was a little tardy. I'd messed up with posting this evening's class slides to Carmen. So they're up there now. I'm going to begin class doing a little bit of touching ideas that we were exploring last time. So if class slides are a resource you use and you looked earlier in the day and didn't see them, if you wanted to double back to Carmen and grab them now, that wouldn't be a bad idea. What we're going to do this evening is we're going to work on a pretty big chunk of the chapter here. Last time, I think the topics that we were looking at were pretty conceptual. They were looking at terms that we needed to think about in different ways and begin to make connections. And then for what we're going to do this evening, I've got a really good sense for the very typical questions that you're going to have, what you should expect to see on the exam. So I think within this one, we can bang through a lot of the different topics here, because I think there's very specific things that we can put together, and I think you're going to be able to do well with those. The setup within this one, before we begin, I look out my window, it's continuing to snow. So my first poll question is, I want to know your view of the snow. 1 to 5. 1 is, I'm so done with the snow. 3 is, well, you can't control the weather. And 5 is, you're willing to say you want even more snow. Now, personally, when I set this poll up, I was initially thinking that, I don't know, I thought I might be, when I saw the poll, I was thinking, I might be like a 4. Because yeah, I'm from Michigan. I'm happy to see the snow. I like it. But the more I thought about it, I think I'm probably a 5. I mean, if we're gonna have snow and I'm in my house anyways, I'm not shoveling it. I say I'm gonna agree with the folks that are saying the 5. I completely understand though if you're a 1, and in fact that looks like the majority that we have here. The looking ahead a little bit, this is what I've done within mastering. So within mastering, I've populated it with questions that we have pertaining to chapter 5. The stuff that we have due on Friday at the end of the week here, that's actually ideas that we would have covered last time. But the stuff that we're going to cover this evening, I've spaced it out and I have it due on Monday and Wednesday of next week. Now, I know next week we don't have class on Tuesday, sort of this new break that they're trying. So these deadlines that I have for chapter 5, I know that I'm going to shift them back next week. My choice right now, I'm trying to sort of balance the opinions I've heard from different people. Some people are saying, yeah, please put them in with the usual spacing that we have, because they're used to whatever their pattern is and they don't want to have a whole bunch due at one time, which I get. But there's others that are like, no, I just need a mental break. I'd rather be able to make my own choice about it. And I also get that too. So I'm trying, as they say, I'm trying to split the baby with this. I'm putting them into my usual schedule that I would be suggesting, but I know next week I'm going to shift them back. So however that works for you, whenever I'm setting deadlines in here, it's not like there's some secret master plan. When I'm setting up the deadlines within this, I'm just trying to spread out the content for us, so it doesn't back up and you don't see it all at one time. But let's see if we can sort of think about what's going to work best with this. Okay, we can sort of negotiate it as we work on it. I'm going to keep it in mastering with the setup that you see right here, but I'm willing to be flexible next week to try to make it so it works for you. Okay. Now, idea that we had last time was we were looking at this description of the potential energy that was due to charges either being similar to each other or different from each other. And what did it mean when they were going to be either far apart or closer together? This is something that you're not going to be doing calculations with, but I've seen questions like this on the exam. We have the idea that when we have an attraction and they're far apart from each other, the particles are approaching a potential energy of 0. And as they come together, they're moving to a lower, more negative potential energy. This is how I've seen this question asked on exams. So it says, consider the charge and the separation of the following spheres, case A, B, C, and D. Looking at those, well, what would you say would have the most positive potential energy? How about the most negative? Which one's closest to a potential energy of 0? So a qualitative analysis of looking at the charges, their magnitude, and how far apart they are to try to answer these questions. So take a second, see if you can interpret this. If you look at these different choices, A, B, C, and D, which one would you identify as having a positive potential energy, the most negative, and the one closest to 0? So the way that we would look at this one, then, we have to first ask, well, what is our reference for our potential energy? Our reference value is when we have the particles and they're far apart from each other. So I'm going to say that looks like the best example would be case D. They're at the farthest distance that I see. What about then of what does it mean to say something has a positive potential energy or a negative potential energy? That comes back to this image that we have right here. As the particles are attracted to each other and move closer together, the potential energy is going down. How do you go down from 0? You make it more negative. That's saying that this bottom region where there's an attraction, that's corresponding to a negative potential energy. If the charges are alike, both positive or both negative, then as they move closer together, the potential energy goes up. So I've rearranged these and I've put them in order for what I would then say would match up. I have at the top an example where they're both positive, both the same charges, means that it's repulsion. It's a positive potential energy. I took the one where it's furthest apart. That would be the one that would be closest to 0. As they're starting to come closer together and there's an attraction, if it's either +2 and -1 or +2 and -2, the potential energy is going down. And the two factors that affect the magnitude of that, the strength of that attraction, it's the charge and the distance. So if we have two cases where they are I tried to make them the same distance. If we have two cases where they're the same distance, the one with the larger charge has a larger magnitude for the potential energy. So in that case, it would be the most negative. That's how I would be interpreting this part. Now, within this one, when I say this is a typical exam question, I've seen this topic asked this way. So in tonight's talk, as we go through, I'm going to try to specify for you, designate ones that I know are really typical exam questions. I'm putting it in red here. Very typical exam question. Looking at things like the charge and the distance and qualitatively determining how that relates to the potential energy. Let me ask you this one. Let me shoot you a question on this one. Do you think you can do this? Would you say you're confident that you can answer a conceptual question like this involving the charge, the distance, and the potential energy? Take about 5 more seconds. Okay, sharing results on that one. It looks like we're neutral and then maybe trending a little bit positive that you think this is something that you can do. That tells me I'll provide more examples for you to practice this. Okay, I think that this one, it's a concept that we talked about last time that I know is a little bit difficult to get your head around, and this is the first time I've had you practice it. So this tells me, let me provide more examples for this. In subsequent classes, this is something that we're going to continue to practice. Another thought that we had when we were connecting this now to the nature of bonds. If I have the particles of matter stuck together, it's going to take energy in order to separate them. So if I have things that are bonded together, it's always going to take energy to break apart those bonds. Bond breaking is always an endothermic process. If I add heat, if I add energy, I can break it apart. Conversely, if I'm going in the opposite direction, if I have the particles of matter attracted to each other but spread apart, when they're coming together to form bonds, that's an exothermic process. I looked within the skate park here to sort of try to explain a little bit what's going on. So it turns out we're going to see that some bonds are stronger than others. The attraction between the atoms in the bond, different bonds have different strengths. If you have a strong bond, a stronger bond leads to a lower potential energy, a more negative potential energy. They're more tightly held together. So I could show that here with this skater. He could initially be stable going back and forth in this part of the skate park. But if I add a little bit of energy, I can shift him over the hump into this part. And notice how now the potential energy can go much, much lower. So here he is going back and forth. It's as if he has a particular potential energy there. If I add just a little bit more energy, I'm going to grab him and take him over the top there. Now he can go to a much lower potential energy. As he continues down, lower and lower potential energy, kinetic energy keeps going up. This is how that you can have bonds of one strength relate to bonds of another strength. That's what's happening when I'm blowing up this hydrogen-oxygen balloon. I'm adding just a little bit of energy in the form of a match, and then kaboom, the products then have a lower potential energy than what the reactant started with. So if you think about this in other classes that you might have heard, if someone says, well, you get energy from eating a banana, or you get energy, it's somehow released from burning gasoline. What they're really saying is that the products in the reactants, when we compare those, we find that there's a difference in potential energy. They're saying that after that reaction takes place, the products are at a lower potential energy than the reactants were. And it is that difference where the energy comes from. So it's a mistake to say you get energy by breaking a bond. You always require energy to break a bond. This explosion here then is comparing the products with the reactants. Now, another idea that we had last time was when we were defining different systems. One that we brought up a little bit was this idea of a closed system being a piston as an example. So as we looked more last time, we saw that energy can be transferred involving either Q or W, the heat or the work. If we look at a piston, well, the volume can change in a piston. This means that the pressure volume work, it could be relevant in this scenario right here. In chapter 5, we see a lot of pistons for this reason, because they want to set up scenarios where we could explore pressure volume work. It turns out that pistons like this, the ideas in this chapter, they came about because of scientists studying pistons. Engineers, physicists, chemists, all in the Industrial Revolution, when they're looking at different steam engines and trying to optimize their performance. That's where the ideas within this chapter came from. It was really them working with the technology of the age, which was really one of pistons. Now, one that they then came about, this was in the 1800s then, first law of thermodynamics, where they were looking at then the behavior of these pistons. This brought us to a couple ideas that we had last time. So we described something as the internal energy, which was the sum of all of the potential energy and all of the kinetic energy for all of the particles that you were looking at. And we said that that would be a value that we don't calculate in an absolute term. We typically look at how it changes due to the heat, Q, or the work that was involved. We said when the Q value was positive, that meant that we had an endothermic process, heat was going into the system. And when Q was negative, it was exothermic, heat was leaving the system and going into the surroundings. Most of the time, students do really well understanding these heat conventions. We also, though, have a way that we can describe changes in energy involving work. The work involves pressure volume work. When work is positive, now work is what's going into the system. The volume of the system is getting squished smaller. We're doing work on it. If the volume of the system gets larger, then the system now is doing work on the surroundings. If we look at the volume, that is a key thing to think about with the work. So we did a scenario like this last time. The scenario was, suppose you put water in a bottle and you call that the system. It's placed in a freezer, the liquid turns to ice, and the bottle breaks. And we went and we assigned Q and W in that case. For these questions, key for its skill is we have to read carefully what is being called the system. In this case, what was being called the system was the water that we had in the bottle. So I say we have to look at that closely because we have to think about, well, what are we seeking then to analyze? So the water went from a liquid to a solid. That's an exothermic process. You have to remove the heat from the liquid to turn it into the solid. So the Q value would be negative. And the system did work. The volume of the water increased and cracked the bottle. So the work there would be negative. I'm going to put a box around this one. This is another very typical exam question. Very typical of having a scenario and seeking to assign Q and W. I'm going to send you a polling question on this one. When it comes to this particular skill, how confident are you that you can do this? Given a scenario, do you feel like you can assign Q and W?
Am I able to ask a question
Yeah, go
about
ahead.
work? So work only talks about the system, correct? Even though things are transferred into the surroundings, it's about the volume of the system.
Yeah, I think that it's going to be easier if we can narrow it down and be talking about the system and consider how the system can either get bigger or smaller. The volume can get larger or smaller. And the reason I say that is, like if we had this case right here of putting water in the freezer, if we said, oh, let's say it's all the air that's around it somehow, I'm not sure how I can really measure that. The reason that we do this division between system and surroundings, in a way, the system is what we can measure, and the surroundings is everything else outside of that.
Okay. And then this is kind of jumping ahead, but in calorimetry, is it always the assumption that the water is the surroundings?
Our setup within that will always be able to look at our thermometer, which is placed in the water. And by looking at that, that will always be, we can always do the same plan with that all the time to determine whether we're looking at an exothermic or endothermic process. So if the plan that we described tonight, that's always going to be appropriate. So within this setup right here, it looks like we're, again, sort of in the 3 to 4 range. In this case, I've got another example. So let's try another example. How about this one? So this one says a balloon is placed on top of a bottle. Let's consider the balloon and the bottle to be the system. Now I'm going to take that balloon and the bottle and I'm going to put it on a hot plate. After a while, it's sitting on the hot plate. I see that the balloon has now inflated. Give this a try. See if you can assign Q and W for this. Here's another scenario. As this one's coming in, I see within the a chat here, a question about what does it mean to say work goes into the system? When I say work goes into the system is being squished smaller. So the air around it, the surroundings around it, my hands around it, if I squish the system smaller, then I'm doing work on that system. That's what I mean by that. And again, if we just observe what's happening with the volume, that tells us all we need to know. Okay, so within this one right here, if I look at this scenario, I would say that heat is going into the system in this scenario. It's on the hot plate. The system's temperature is going up. I'm heating it up. In the process within this, it looks like the volume of the system is increasing. The balloon is now pushing against the air that was around it. So the system is now doing work as the volume expands. So I'm choosing this one as an example because in the previous examples, they both had the same sign. Okay, in both of them, the Q and the W were both negative. In this case, we've got one positive and one negative. You can have any different combination on this, okay? But in each of these, you just simply have to first say, okay, what is the system? What do I see taking place in terms of the heat transfer? And what do I see taking place in terms of the volume? Here's another one that I've seen that is on the same topic. This is a question that was, I suggested that people might want to take a look at. This is an end of chapter 1. So within this one, they're giving different scenarios, and they say that the length of the arrows represent the magnitude of Q and W. So as I look with this, which of these are endothermic? Endothermic only refers to the heat. So I only have one example in which heat is going into the system. So I'd say this would be an example that's endothermic. Second one, for which of these properties would the change in internal energy be negative? That means it's going down because you have more energy leaving the system than going in. It doesn't look like that's taking place in any of these examples. I think in each of these examples, they're trying to show that overall the net internal energy is going up. Maybe because work is being done on the system, or more work goes in than heat goes out, or more heat goes in than work comes out. So this would be one I would say is conceptually trying to look at the relationship between internal energy, heat, and work. Here's another one that I've seen where they actually put some numbers on it. That's shown at the top. So instead of showing arrows, they're giving actual values for Q and W. I'm putting this whole thing in a box too. Okay, this would be one that I would say from the start of the chapter as far as a representative question. Now let's move on to some new ideas. So within this one, let's begin by looking at these 3 particle representations and try to rank them in terms of internal energy. Remember, internal energy has to do with all of the potential energy and all of the kinetic energy present. So if I'm trying to rank these, I see that I have thermometers in each one. Okay, so the thermometer is a reflection of the kinetic energy. So by looking at the thermometer, you know the kinetic energy. In this case, the gas has the highest kinetic energy and the solid has the lowest based on the temperature. Then if I think about the potential energy, which one has the highest potential energy? That's when the particles are furthest apart from each other. That would also be the gas. If I were to rank these in terms of internal energy, I'd put the solid at the lowest temperature at the bottom and the gas at the highest temperature way at the top. Now I could transform these from one to another by heating them up, adding heat or removing heat. So take a second, see if you can apply these terms properly. If you go from the solid to the gas, would you describe that as being endothermic or exothermic? And what would be the sign of Q? How about if you're going from the gas to the liquid? Endothermic or exothermic? What would be the sign of Q? Take a second, see if you can decide that. As I think about my everyday experience, I think I have to add heat to go from the solid to a gas, and I have to cool it down to go from the gas to a liquid. So I would say it's an endothermic process to go from the solid to the gas. Q would be positive. and it's exothermic to go from the gas to the liquid, Q would be negative. So if I were to put these in sort of a scale right here, I'd put the solid at the bottom with the lowest internal energy. I could add heat and go to the gas. I could remove heat and take it back to the liquid. Now, within this one, is there any way that I could get the missing step here? Suppose I measured how much heat it took to go from the solid to the gas. And then I measured how much heat that came back when I went from the gas to the liquid. Is there any way that I could get the missing step? Yeah, the missing step would be the difference between those two. What I'm trying to get at here is internal energy is something that's called a state function. With a state function, the pathway doesn't matter. All that you need to know are the different initial and final states, and you can put them together to get the missing link on them. To give you sort of an example within this one, let's say you're mountain climbing, Mount Kilimanjaro, and you go from the base camp to the summit. If you want to measure the change in elevation, you could compare where you start out at the base and where you finish at the summit. Change in elevation would be a state function. It doesn't matter if you go in a straight line or a curvy path. As long as you compare where you're starting out and where you finish, the change in elevation would always be the same. The pathway doesn't matter. Elevation would be an example of a state function. The pathway doesn't matter. All you need to know is where you start and where that you finish, and you can take the difference between those. We're going to see here within chapter 5, that's going to make our problem solving really beneficial. It's going to be a really beneficial thing to have things be state functions. Internal energy is an example. Now, what I'm going to do here is I've ranked these in terms of internal energy. I'm going to switch terms a little bit. Instead of calling it internal energy, I'm going to introduce a term enthalpy. Now, the reason I'm introducing it here is a lot of the same conceptual picture we have as far as what does it mean to say something has a low internal energy or a high internal energy. Those same rankings, the same way that we think about them, thinking about enthalpy works in the same way too. But what exactly is the enthalpy? So enthalpy, this is where the idea comes from. A lot of times the experiments that we do in the lab, the only work that we would care about would be the potential PV work that could take place. If you do your experiment and it's just open to the atmosphere here, as you do the experiment, the pressure is constant. It's atmospheric pressure opposing it. So this would be a case where the pressure, it's staying constant for us, the external pressure. Enthalpy is the heat that we have either coming or going when we're looking at constant pressure. And that's why a lot of times you see it either given the symbol H or the symbol Q sub P. Q, after all, was heat, and the P part is saying, remember the pressure is constant. So the definition on this is the heat being transferred when the pressure is constant. I don't know if you'll ever have to use that definition, but this is going to be how we think about heat coming and going within chapter 5. It's under the conditions that we often see in the lab, which is the pressure is constant. So if you want to think about the enthalpy, the change in enthalpy as the change in the heat, that's going to be a pretty good understanding. Turns out that we like enthalpy because it is a state function, so the pathway doesn't matter. When we use the terms endothermic or exothermic, we use those for Q. Those will also work for the enthalpy. So for the rest of the chapter here, when I'm talking about the heat that's involved, it's going to be described as the enthalpy. So let's now see how we can begin to use the idea of enthalpy in a few different ways. That's really the rest of what we're going to be up to tonight. We're going to be looking at aspects of the enthalpy. So first of all, we can see an enthalpy value associated with a reaction. So in section 5.4, we see these enthalpy values as they're associated with different reactions. Now, enthalpy, the different things that I'm going to touch on here, we're going to see how this is important. first set here. Enthalpy is an extensive property. If you double the amount of matter involved, you double the delta H for it. So think back when I exploded this hydrogen oxygen balloon, at least the picture of it. When I explode that, kaboom. If I had a really big balloon filled up the same, even bigger explosion. Enthalpy is an extensive property. The amount of heat involved depends on the amount of matter that you have. Second is, if you reverse a reaction, you change the sign of the enthalpy. So what that is saying right there is the signs that we attach for things like Q and W tell us the direction. So if you keep the reaction the same, but you just reverse it, then what you've done is you're reversing your description for the heat. So you can keep the magnitude the same, you just change the sign on it. I'll show you what that means in just a second. When we're looking at these reactions, the state of matter is going to be important. And once again, it's going to be really helpful that enthalpy is a state function. So as we begin to think about this one, this is a particular description that they show a little bit in chapter 5, and we're going to look at it more later on. So this is what is called a reaction progress diagram. On the left-hand side, it's showing the reactants, and it's showing as the reaction takes place, as you go left to right, what's happening to the enthalpy. So at the top, this is the reaction that we're going to be looking at. Hydrogen plus oxygen to give me H2O. This is the explosion that I have. So initially, the hydrogen and the oxygen have a particular enthalpy value. I mentioned that we can sort of think of that enthalpy here as like the internal energy. You could say the reactants have a certain amount of internal energy. It always takes energy to be breaking the bonds that we have. Bond breaking, we said, is always endothermic. So if this reaction right here, if initially I have molecules and I want to break them apart to get the atoms, that's going to take energy. So that's why it's shown going to a higher enthalpy value. Now this right here, this reaction, I mentioned it's an explosion. So I'm going to add that information here at the top. When we have the enthalpy for a reaction, it shows up at the end of the reaction, delta H equals negative 241 kilojoules. That's the heat that's involved with this reaction. It's an exothermic reaction. Now we might say, well, where's the exothermic part? It was endothermic to take apart the hydrogen and the oxygen molecules. It's because when they come back together now to form the H2O, that is the exothermic part. When you have an exothermic chemical reaction, you'll have an initial bump, and then it comes back down to a lower enthalpy value. And the change when we're comparing final minus initial, it's between where we started and where we finished. The difference between those, final minus initial. That difference right there, that's what makes this whole reaction exothermic. Now, I mentioned that it is a extensive property. So look at this example. So we've got the combustion of methane gas, CH4, with O2 gas. It's said to be exothermic, and it produces 890 kilojoules of heat for every mole of methane. So first thought, what would a balanced chemical reaction look like with that? So this takes us back to some ideas that we had back in chapter 3 for combustion reactions. This would be my description of a balanced chemical reaction when I take 1 mole of methane gas reacting with O2 gas to give me CO2 and H2O. CO2 gas, H2O liquid, those are the products that I have in this combustion reaction. It says that for every 1 mole of methane, it releases 890 kilojoules of heat. So in this balanced equation right here, I have a coefficient of 1, it turns out here for the methane, and 890, that's the amount of heat that's involved. The sign right there tells me it's exothermic. So when we have these reactions written, if it's positive or negative, that's telling me whether it's an endothermic or exothermic reaction. Now, initial thought right here, when I have this one, we've been practicing balancing chemical equations. I think you're good with that and you're able to come up with the correct coefficients. A lot of times students though, they struggle with, okay, you've just added some additional information here. How does this fit in? The way this fits in is, this is saying that if you have 1 mole of methane, 2 moles of O2 to form 1 mole of carbon dioxide and 2 moles of H2O, this is the amount of heat that's produced. So we can use that to say, oh, well, what if we have a different, or we have a particular amount of the reactants in grams, let's say. How much heat would be involved then? So what we're doing now is we're connecting the amount of heat that's involved with the reaction stoichiometry. So a key thing that I've seen when students struggle with this one is they see that number at the end, but they don't know how to make sense of it. The key thing we want to remember within this is that when we see that information at the end, the coefficients are mole amounts. When we see the number at the end, the coefficients are mole amounts. So this is how I would describe what's going on, okay? I would say when 1 mole of CH4 reacts with 2 moles of O2, it produces 1 mole of CO2, 2 moles of H2O, and it produces 890 kilojoules of heat. So what I've done right there, and usually when I have my big class of 300, we all chant this together, because what I'm trying to emphasize is the coefficients are in mole amounts. If you have 1 mole of methane and 2 moles of O2 reacting, it will give you 890 kilojoules of heat. If you don't have 1 mole and 2 moles, it will give you a different amount. So that's what this question is asking. How many kilojoules of heat would you get if you use 24 grams of methane? So what I'm going to do is I look at the periodic table and I see that, oh, 1 mole of methane is 16 grams. So I have more than 1 mole. They're asking about 24 grams. The molar mass is only 16. So I have a little bit more than a mole. I know that 1 mole gives me 890 kilojoules. Okay, so if I use 24 grams, I get 1,340 kilojoules produced. It's scaled up more because I used more than 1 mole of it, because it's an extensive property. Tell me in the chat right here, do you have questions on that part? Yep, we can just be considering enthalpy as the heat that's involved. It's the heat, officially, it's the heat that's involved under constant pressure. Now, there's a question within here as far as how would I interpret the sign, or how do I use it? And there were a lot of questions I saw within perusal on this part. When we are thinking about the different quantities like heat or work here, I've seen this analogy where they said, well, consider it like money going into or out of a bank. You can say, okay, I have $1. $1 is not positive or negative. $1 is just $1. If I put it into the bank, I want to say it's positive and my account's going up. If I pull it out of the bank, I want to say it's negative and my account balance is going down. But the thing itself is just $1. So what I'm trying to get at within here is the heat that's involved. We have both the magnitude of it, the amount, and we have a sign that tells me the direction. So I'm not getting too hung up on that at this point. When I say that the amount of heat that's being produced, this is the quantity of heat that's being produced. But I agree with your analysis of saying we can communicate whether it's being absorbed or emitted based on the sign. It's not a big hang up, but that's sort of what you see if you, it looks like there's a combination of how they treat it within the chapter, okay? Now, take a second within here. If you have methane and oxygen gas, it undergoes this combustion reaction. Take a second, where is the heat coming from? Does it involve breaking bonds in CH4, breaking bonds in O2, forming bonds in CO2, or forming bonds in H2O? What part of the process is exothermic? comes back to this idea. It is the forming of the bonds that is exothermic. I think within this combustion reaction, you initially had to break the bonds, but the products are at a lower potential energy. And it was going from the reactants to the products being lower in energy. That's what released the energy. Now, within this one, as I'm trying to designate learning objectives or things that you might be asked to do, I think both of these are legitimate questions that I've seen. I'm really confident that your next exam is going to have a question that is relating the stoichiometry of a reaction with the heat that's involved. There's almost always a question on that. And we almost always have a question back to this conceptual one. Which part of a reaction is endothermic and which part is exothermic? So both of these, I think, are learning objectives. So if you pause for a second, I would say right now, we've already covered what, maybe 6 different exam questions? There's a lot of different ones that I'm really clear that we always ask those. So let's see if we can add to that. Another one that I'm 100% sure you're going to have on your exam involves what's called Hess's law. So let me show you how this one goes. It's almost like sort of a puzzle within this one. So within this one, the idea is that the enthalpy change values, a lot of these are tabulated. You can look them up, but not everyone in the world is listed there. Many of them are listed, but what's cool is, remember, enthalpy is a state function. We can combine the ones that are listed. And by combining the ones that we do have listed, we can solve for reactions that we might not even be able to do. So the way that this works, it's sort of like a puzzle again. It's taken the fact, it's taken advantage of the fact that enthalpy is a state function. We can put together the parts however we want, as long as it still takes us from where we're starting from to where we finished. So this is sort of an example. So within this one, it's saying you could calculate the enthalpy change if you're going in this combustion reaction of the methane plus the O2 to give the CO2 and the H2O. This reaction right here, you can see that you're going, and it has a value of 890 kilojoules. What if instead of going from where you start to the finish, what if you think about it taking place in 2 steps? Let's say you go and instead of going all the way to the bottom, you just went down through this first green arrow. You said that what was actually taking place was you were forming carbon monoxide, water, and some oxygen gas. And then from that point, you went all the way down to the bottom. So instead of going in one step, you went a portion of it and then another portion of it. You should be able to add those together and recognize that in both cases, you're starting at a particular spot and you're finishing at the same spot. So the total difference in energy, it should be the same whether you did it in 1 step or 2 steps. So the way that this is showing up right here, you have for that first step, what they're calling delta H sub 2. That involves 607 kilojoules. That got you to this step right here. Now, if you start from that one, you could go all the way to the bottom. So what I'm doing is I'm putting on the left-hand side both of these sets of reactants. I'm putting all of the reactants that I see in these combined ones all on the left-hand side. I have the ones that I started with. I have the ones that I get along the way. This whole set right here, these are all of the reactants for both of those procedures. I can do the same thing for all of the products. I've listed a whole bunch now here, but I've got some that are found both on the left-hand side and on the right-hand side. These got me part of the way. These are what I'm then picking up. So I can cancel those out. Those are found on both sides. If I want to know what the net reaction is, I'm going to cancel the terms that I see on both the left and the right-hand side of the arrow, and I'm going to see what I'm left with. What I'm left with, it should be where I started and where I finished. If I'm doing that, I can now add together the enthalpy values. And notice how added together, I've got to be careful within my setup within here. It takes me, and here I am saying you got to be careful. And it looks like I'm messing up within this one. Looks like the two values, right, are 607 and 283. All right, that looks better now. So by adding the two steps together, I can see it doesn't matter if I did it in one step or two steps, I still end up at the same spot. So within a Hess's law, sort of our puzzle here, this is what we're going to be doing. We're going to be considering, well, what would it mean if we were to do it in one step? Or what would it mean if we're doing it in different ones that we combine together? Let me show you the setup for this. I'm going to show you like 2 or 3 examples. Okay. So here's one where I just am showing in general terms with A's and B's. This is how these questions are typically set up. Notice there are 2 provided reactions. 2 provided reactions with their enthalpy changes. And then it says, what is the enthalpy change for like this other target reaction? The game of this, the goal of this is we need to manipulate the provided equations, the provided reactions, to get the one that we're trying to find the answer for. We need to combine the provided ones, add them together to reach our goal. And when I say we have to combine them, we have to manipulate them, because right now, if I just add these together, what would be on the left-hand side? I would see a total of 3A and 7B. Well, that's not what I want. Those are not the right reactants. I need to make it so that when I add them together and they cancel, it results in the target equation. Now you might think, well, how do you begin to do that? How do you make it so that when you add them together, they correctly cancel? Let me show you my strategy. So if I look within this one, I am going to look to try to find a feature that I see in a provided equation and in the target equation, and I know that if I get that one placed correctly, it's going to be in the right spot. So what do I mean by that? If I look within both of these, I see a whole bunch of A's and B's in both reactions. Those are going to be a mess. But what about this AB2? It's only showing up in this one provided reaction, and I know where it needs to go. It needs to be a reactant with a coefficient of 2. If I get that as a reactant with a coefficient of 2, I know that that entire equation is set up properly. Similarly, if I look at the second one, A2B5, that's the only time that it's provided here, and it's already as a product with a coefficient of 1. So that equation's already fine, but I need to manipulate this first one. I need to take that reaction and reverse it, because I want to make it so AB2 is now a reactant. And I need to double it. I need to double it to make it to have a coefficient of 2. Now, when I double it, I've got to double all of the coefficients. So what I'm going to do is I'm going to take that reaction, I'm going to write it in reverse. And I'm going to double all of the coefficients because I want it to have a coefficient value of 2. So think back to our rules. What do we do to the enthalpy value when we reverse a reaction? We're going to change the sign on it. What do we do if we double the amounts? We need to double the delta H as well. So if I take this and if I've reversed that and doubled all the coefficients, instead of having a value of -35, it's now a value of +70. I have reversed it to change the sign, and I doubled it because I doubled the coefficients. Now let's take those two just to see if it works. I'm going to take the ones that are in the box, and I'm going to add them all together. On the left-hand side, I see 2 A's, 5 B's, and 2 AB2s. On the right-hand side, I see an A2B5, 2 A's, and 4 B's. So it looks like the A's will cancel on each side. I'll have a leftover B on the left-hand side. And I have the other terms exactly. That's exactly what I needed within my set. Okay. Before I go on to another example, questions in the chat for me on this one. Do you get the general idea?
Can you go back to the last slide?
Sure.
Mr. Clark, can I ask a question?
Yeah, please.
What if one of them was positive, the enthalpy was positive?
And when we're doing the, are you saying that when we then combine them?
No, like in the question itself, if one of the equation had a positive and the next one had a negative, how would you solve that? Would you solve it the same
Yeah,
way?
that won't, you'll definitely see that at times. So let's say I were to add them together, and in this case, I think I am adding them together where I've got a positive and a negative. Is this what you're saying? Because I'm saying, oh, -90, +70. When I add those together, it becomes -20. I'm looking as I add it together, you know, those two terms. Is that what you're asking or something different?
Yeah, because I was solving the questions that you gave us in the mastering today, and we had some questions like this, but I was getting the answer wrong when I tried to add them. So I was just wondering.
Let's see. I'm going to mention a couple more examples here, but I'm not sure I'm going to answer your question. So if I don't get to that, because I'm not sure exactly where you were going wrong with it, let's share it with me in another way, okay?
Okay.
Yeah. Let me pull up another one here. And I want to sort of step through the setup and then how it gets solved. So once again, here's another Hess's Law one. They're giving you two different equations to manipulate. And it says, use the provided ones to come up with the unknown one. Hess's Law questions, really easy to recognize because they're providing a couple reactions and asking about the unknown. And for the unknown one, you need to manipulate the provided so that when you add it together, it correctly cancels. So this is a sample exercise from the book. This is how it then shows if you add it together, you get the correct answer. Let me show you how you would get to this point. Okay, this was how it set up the question. It said, here's the provided question, and at the bottom, this is how it worked it through. So again, if I'm going to do my problem solving on this one, I'm going to ask, how do I manipulate equations 1 and 2 so that when they add it together, they'll cancel correctly? So if I look within this one, as they were added together, there was a CO2 on one side, CO2 on another, those would cancel out, and everything else remaining works with the target equation. But how do we get to that one? I would be looking to say, okay, in this first provided one, that's the only time I see carbon solid. And I know that the carbon solid has to be a reactant with a coefficient of 1. So I can just write that equation as is. It's got to work because that's the only way carbon solid shows up in the right spot. If I look at equation 2, well, I don't want to mess with the O2 because I need that to somehow cancel. I don't want to mess necessarily with the CO2 because that's showing up multiple times. But the carbon monoxide, I know that that has to be as a product with a coefficient of 1. So let me take that whole reaction, reverse it, and that means I reverse the sign. So instead of being negative, it becomes positive. That makes it so if you add it together, everything cancels properly and you end up with the right value. This idea, the Hess's Law, I'm sure Hess's Law problems, you'll absolutely have one of these on your next test. Let me show you one more within this one. So within this part, notice within this case, there's a provided reaction that you need to get to. This one, it has 3 sets. So there's a target reaction with 3 different ones that you need to make it work. Take a second. This is going to be a mess unless you sort of have a plan. I've tried to point out what my plan was of looking for unique features. Take a second, see if you can analyze this and figure out what would be the unique features. Which ones would you look at so that they end up being in the right spot?
Just for a clarification, we will be given the equations needed on test, correct?
For Hess's Law within this one, they always give you the equations No more, no less. If they give you 3 equations, you got to use all 3. If they give you 2 equations, you got to use 2. They make life perfect in that sense. They will never give you too much information or too little for a Hess's law problem.
And
Okay, thank you.
they'll give us the enthalpy value for them as well, correct?
Yep, this would be right here would be a very typical equation, a very typical question.
Thank you.
Yep. So if I'm looking within the features right here, how I would solve it, I need to have carbon solid. I see that only showing up 1 time. So that reaction, that middle one, it must just stay, well, excuse me, it's showing up, that's the only time, but it needs to have a coefficient of 2. So this entire equation must need to be doubled. Doubled all the coefficients and double the delta H. How about with the H2? That one looks like it needs to be a reactant with a coefficient of 1. It already is, so that reaction's fine. This one right here, coefficient of 1 for the acetylene, but I need to reverse it, so I changed that sign right there. My approach within this one, when I'm solving a Hess's law one, I told you my strategy of what I look for unique, and then I just write it out, and it always works, okay? Definitely something, though, that takes some practice to make sure it's working for you. Tell me right now, what's your view of Hess's law? I'm going to send you a polling question on that one. Are you in the category of 1, you have no idea how to do it? 2, you think you need some practice? 3, you got the idea, but you want to really perfect it, or you already knew how to do it? As was mentioned, so there's some examples of this I know within mastering. If you tried this and it's not working out, just take a screenshot of what you did. Show me your work. Send me your work right here, and it'll be easy for me to check for you. Okay, so the 2 questions that showed up within that one was, might you have examples where you have to triple or quadruple a reaction? Yeah, you could have any kind of adjustment that you have to make. You might have to triple it, you might have to cut it in half. Anything to take from the target one and the provided ones to manipulate it. So I've seen that within the set. And then the math, as far as how you then combine it, this might be the cleanest example for that. So notice within this one right here, they're showing that these were the 2 for how they'd manipulated it, and these are the resulting changes to the delta H. Now they're just taking this and adding it together. They're adding it together and canceling the missing terms or the extra terms that you have amongst the reactants and products. And then the delta H value, they're just adding those together. Negative 393, positive 283, add those together, it's a negative 110. Okay, let's move on to one more idea within here. This was one that was in a pre-class video involving aspects of calorimetry. So we've looked already at some conceptual ones, I would say at the start. Several different sets of problems here in 5.34 in Hess's law. Calorimetry, this I'm putting in a different category because you have some different ways to sort of think about this. So let's look at, first of all, the phenomena. So what happens if you add heat to matter? I think right now we'd say you got 2 different things that could happen. You could have a phase change take place. You could take an ice cube and melt it, for example. Now, it turns out an interesting thing is a phase change takes place at a constant temperature. We're going to talk about that more. But that tells me that a phase change, if it's a constant temperature, a phase change must involve a change in the potential energy. We must be taking it, and we can have a phase change at the same temperature. Same temperature, if the temperature tells me about the kinetic energy, if I'm adding heat to it, that tells me a phase change must involve potential energy. We're not going to look that much at phase changes until I think it's chapter 11. In this one, we're spending more time looking at what happens if the temperature does change. If the temperature does change, that tells me that the kinetic energy is changing. We can think about how matter then responds to heat going into it and the temperature changing by thinking about it in two different ways. We could think about it using what's called the heat capacity or the specific heat. Let's look at the heat capacity first. So I would say a particular object has a heat capacity. When I say particular object, you have a heat capacity. Your pencil has a heat capacity. I'm looking at my dog right now who's trying to get out of this room. The dog has a particular heat capacity. A particular object has a heat capacity. Tell you what, hold on one second. I'm going to open the door. I think he wants to leave. Okay, I'm back. So now a specific heat, instead of having that be for a object itself, that's oftentimes for different pure substances. Let me show you the difference within this. So here's a scenario problem. A lot of times these are set up as scenarios. This one says you've got a certain mass of this hydrocarbon, that's quinone, and you're going to explode it in an object like this, what's called a bomb calorimeter. You're going to measure how the temperature changes. And from that, you're going to learn how much heat was involved in the combustion. So I'm bringing this one up. This is giving me information about the heat capacity. We said the heat capacity was for a particular object. The heat capacity is for this whole object right here. The metal that's involved, the water that's involved, the wires, everything within this one. This object has a particular heat capacity. If you add heat to it, the temperature changes. That's what the heat capacity value is telling me. So as we work through that scenario, I'm going to work through a couple of them. Let's see if we can answer a few different questions. So this first one, given that setup right here, how much heat was produced in the experiment? I see that I have a heat capacity value and it tells me how much the temperature changes. So I'm first of all going to calculate, well, how much did the temperature change? Change by about 7 degrees. Temperature went up during the process. I can now use that with the heat capacity term because the heat capacity tells me for every 1 degree, it would involve 7.854 kilojoules of heat. I had 7 degrees, so I've just multiplied that together to figure out how much heat was involved. The heat capacity there, it's just a scaling factor. It's discussing how much heat is involved to change it by a degree. Now, I can express that then in two different ways. It's asking, okay, how much was produced for every gram that I had? Well, I got 56 kilojoules of heat when I use 2 grams. This would be expressing it per gram of the reactant. How about expressing it per mole? Well, I just need to figure out how many moles 2.2 grams is. And now I could express that in terms of how many moles is involved. It's an exothermic process. So if I wanted to write that in an equation, I would say that it would have a negative sign on it. So what I'm trying to do within the math, what I'm trying to set up here, these different experiments involving calorimetry, they're almost always set up as scenarios. There's a certain amount of heat that's involved, and then they ask you to express it in different ways. In order to determine the amount of heat that's involved, we look to see how the temperature changes. And with that information, we then either use a heat capacity or a specific heat value. Let me work through a couple more examples within this, but that's sort of conceptually how we're doing the same thing each time. This one right here, whether it's one looking at the total heat capacity or a calorimetry one, I'm pretty confident you'll have something like that on your next test. In this scenario, it was set up so we knew everything about the calorimeter and we were learning about the reaction that was taking place in it. Here's another way that I've seen it asked. This one says, oh, okay, when you're using quinone, the heat that's involved in its combustion is negative 2750 kilojoules per mole. If you analyze 0.02 moles of it in that setup right here, the temperature changes by this amount. Now tell me, what would be the heat capacity of it? what would be the heat capacity of the calorimeter? So in this case, you know everything about the experiment that's taking place in it, but they're asking, okay, tell me about now the heat capacity of this. Let me show you how we'd set up that one. So the heat capacity is typically in kilojoules per degree C. Let's see if we can set up the rest of the experiment to learn what would be the scaling factor here in kilojoules per degree C. Well, we know that the heat that is involved is 2,750 kilojoules per mole, and we use 0.02 moles. The temperature changed by 13.7 degrees. So I would put that in the denominator. Notice when I do my math across now, I'll end up with a certain number of kilojoules per degree, and the mole amounts would cancel. So this would be another scenario that I've seen. The first one was we knew everything about the calorimeter that we were using, and we solved it to say something about the reaction that was taking place in it. Now this one, they told us the heat that was involved with the reaction, and instead now we're figuring out something about the calorimeter itself. I've seen questions like this as well. The one that I had it step through within this one is one where we're looking here at the specific heat. So notice the specific heat, these are oftentimes for various pure substances. Methane, H2O, aluminum, stuff like that. This would be provided information for you. Okay, you don't have to memorize specific heat values. The only one I know from using frequently is water. This would be provided information. Notice how the units are a little bit different than for heat capacity. Heat capacity was like kilojoules per degree. Specific heat also includes a mass amount because it works not just for that object, but for any amount of that. It would work if you had 50 grams of water or if you had 1,000 grams of water. This description here is a useful way that oftentimes you see for how it fits together. You have a certain amount of heat that's involved, and it will change the temperature of the water. It would change the temperature of the CO2. That change has to do with the specific heat, that's what CS is, and the mass that you have. This right here, I've taken the specific heat times the mass. Notice how the units would cancel. You'd have a certain number of joules per gram K times the temperature that you have, and that would tell you the number of joules that were involved in the experiment. Using this equation right here, this relates the heat that's involved and how the temperature changes. I'm going to put a box around that one. I've seen exam questions simply on this topic right here. Here would be some examples. So notice within this one, the specific heat is given for the substance. And the question is, well, how much heat would be involved if you wanted to change a certain amount of it by a certain temperature difference? So what it's saying within here is use this provided information, put them into this expression right here. A somewhat more involved one is when we're doing these experiments involving what are called coffee cup calorimeters. That idea of using the specific heat, that's one of the steps involved in the process. This is what I stepped through within the class video. Within this one, it says, assume the specific heat's the same as that of pure water. That would be a value that would be given for you. When I'm looking within this experiment right here, I solve this by looking at 3 different things, and I do it in this order. I first ask, is it endothermic or exothermic? Then I ask how much heat is involved. And then I look to see how it's supposed to be reported. Anytime I have it set up this way, this is sort of my plan, and I execute it the same each time. So first of all, is it endothermic or exothermic? I'm going to look at the thermometer for that. This tells me that when you did the experiment, it got colder. If the temperature goes down, that tells me it's an endothermic process. How do I make sense of it? Let's think about it this way. We've said that these explosions that I do, kaboom, those are exothermic. You do the explosion, kaboom, temperature goes up. So if you do an experiment and the thermometer goes up, it must be exothermic. If you do the experiment and the thermometer goes down, that's the opposite. It's endothermic. So if you look at the thermometer right away, it will tell you if it's exothermic or endothermic. Kaboom, explosion, temperature goes up is exothermic. Getting colder, temperature goes down, that's endothermic. That's how you can make sense of using the thermometer. Second, how much heat was involved? Well, let's look within the scenario. Here's our expression for that. We have a specific heat value. It says use the same as you'd find for water. You need to know the mass that was involved and how the temperature changed. We want to be careful within this one. The mass involves the entire solution, because what we're doing in this scenario, we're taking a salt, we're putting it in the water, it dissolves. All of that is now the solution. So the entire mass is changing its temperature. That's why I combine both of the parts. And how much does it change? It's changing by about 5 degrees. If I put that together, I can figure out how much heat was involved in the experiment. And then my last step is, how am I supposed to report this? Sometimes they ask it per gram, sometimes they ask it per mole. So I get to the end and I ask, okay, how do they want me to report it? In this case right here, I'm reporting it per mole. So I figured out how many moles I had of the reactants. That was that 4.25 grams of it. I figured out how many moles that I have, and I'm reporting it now in kilojoules per mole. At that very last step, that's when I make sure that it's consistent with being either endothermic or exothermic. The only time I really make use of the sign information is right at the end. So my plan here is I look at the thermometer to determine if it's exothermic or endothermic. I figure out the amount of heat based on this expression, and then I figure out how it's going to be reported. Now, I want to close with here, and you've done a great job sticking with me. We've covered a lot of different topics here. I want to close with here with some problems that you'll find in the book that are related to what we talked about tonight. So let's step through them and make sure we can see sort of what category they're in. So this first one, 5.41, it gives me a reaction, and it asks, what would be the enthalpy change per mole of ozone? To me, this comes back to the idea, this enthalpy value right here is when the coefficients are in mole amounts. This is written right now as if you have 2 moles of ozone. It involves 284 kilojoules. If it's involving only 1 mole, oh, we need to scale it down. So this question right here is related to how is the enthalpy value related to the reaction itself. This next one right here, 5.42, these are, I'd put in the conceptual category. It says, without looking at any tables, think about which of these has a higher or lower enthalpy value. I put this as conceptual because how would I begin to answer it? I'm thinking back, remember, we can think about enthalpy as being related, I said conceptually, to like internal energy. If I'm looking at 1 mole of CO2 solid and 1 mole of CO2 gas, can I change the solid to the gas? Yeah, but I have to add energy to it. I think the solid is at a lower enthalpy value than the gas. This is a conceptual one where it's trying to look at those different features. I've seen that before on exams too. This top one right here, 5.43, these are all examples of connecting the stoichiometry with the delta H value. What would happen if you changed the number of grams? How many grams would you need for a certain amount of heat? All of these are related back to the equation. Same thing in 5.47. They're asking, what do the different coefficients represent? One thing that I noticed language-wise in this one, this question asks, okay, what would happen if you reverse this reaction? What would you do to the delta H? Well, we know if you reverse the reaction, you change the sign on the delta H. It asks here in part C, what would be more thermodynamically favored, the forward or reverse? What they're trying to get at there is, in the world around us, exothermic reactions are more favored. They're more likely to occur. That's an idea that we look at a lot more in the second semester, but that's what it's getting at within that one. If you see that question, that's what it's talking about. Thermodynamically favored means the exothermic version of it. Here I give several examples of Hess's law ones. All of these I think are really easy to recognize. Notice the format for them. They're giving you provided equations that you need to manipulate to get to the target. Two provided ones to get to the target. This next one, two provided ones to get to the target. Three provided ones to get to the target. So there's plenty of ones if you want to practice to make sure you got skill with the Hess's law and it's coming together. These very last sets right here, now this is involving specific heat and heat capacity. These would be ones looking at different aspects of the heat capacity or the specific heat. And then here would be examples looking at calorimeters. So I don't know about you, but as I'm looking within these different features and I'm having like 2 examples for each one, I'm thinking to myself, those are a lot of very specific ideas that I need to practice. There's a whole bunch of ideas that are very specific that get us about 3/4 of the way through the chapter right here. So I would say, if you begin to try to apply your knowledge to make sure that the ideas are coming together for you, that you're able to practice them, I think that the learning objectives within chapter 5, it's really clear what the different ideas and skills are. And now it's just up to us to make sure that we can practice it and get it together. What we're going to do next class, we're going to wrap up just a little bit at the end of chapter 5 and begin chapter 6. But that's not going to be until next Thursday. No class on Tuesday because we're all sort of taking a mental break to play in the snow, I guess. Okay. Okay, I'll be hanging around, folks. If you got questions, I know we covered a lot and I really appreciate your attention. If you got questions, I'll be happy to help.
For the units, for specific heat, it says like joules per gram and then minus K. Like,
yeah, the minus part, they're just saying put the K in the denominator too. So it's joule per gram K. One thing within that part too, the size of a degree is the same for both Kelvin and Celsius. So you don't have to convert it to Kelvin. You can just look at the change and that works fine. You can keep it in Celsius.
Okay, and then is it always going to be represented in joules instead of kilojoules?
I think it usually is for the specific heat. And I think why is if you look back at those numbers, they were pretty close to like values of 1 or 3 or 4. And I think they're doing it that way because if you put it in kilojoules, it would mess with you with the decimal point. So it comes out to be a really clean number if they're looking at it in joules.
Okay, so when you're using the